Welcome back, crew. This is a continuation of our 4-3 notes where we are working with inverse trig functions and trigonometric equations. I considered not showing you this because it takes what we've learned about solving trigonometric equations, which is already pretty hard, and it ramps it up a notch. But you are such a bright group that I really thought that you could handle it. It was valuable and it was worth the extra effort. So we're going to take a look at this. I really think that you're going to get this, and you're just going to grow from it. You're going to be really proud of yourselves. I'm going to be proud of you too. So we're going to look at a couple ways to solve some harder trigonometric equations. The first way is when we have a quadratic form. Keep in mind that a quadratic form of an equation is when it can look like something times our variable squared plus something times our variable to the first plus some sort of constant. And when we solve, we always want those quadratic equations to equal 0. So in the realm of trig equations, our variable is not just a single variable, but is a trigonometric function that contains our variable. So to have quadratic form, we're looking for writing an equation with 3 terms in it, where one term has the function that contains our variable squared, and the other term just contains our function. So the first thing we want to do, if possible, is we want to write an equation that has only one type of trig function. Let's look at this example here. This has the cosine squared of theta, where the cosine is one type of trig function, plus the sine of theta, where the sine of theta is a different type of trig function, plus 1 equals 0. That has 2 different types of trig function, and this is going to be easier to solve. We like easier, right? This is going to be easier to solve if we can get only one type of trig function. So let's think about that. Don't we know a Pythagorean identity for the cosine squared, which would allow us to rewrite that using sine? I know, I can hear you. You're saying, yes, Mrs. Key, we do. We know that the cosine squared of theta is the same thing as, right? This is the same thing as 1 minus the sine squared of theta. So we're going to replace cosine squared with 1 minus sine squared, and then we're going to finish this equation. So to that we are adding the sine of theta plus 1 equals 0. So I solved one problem. I have one type of trig function, the sine, instead of 2, but I've created another problem, and now I have 4 terms. But, right, can't we add this one and this one together? Again, you say, yes, we can. So now we have a negative sine squared of theta plus our sine of theta plus 2 equals 0. That's quadratic form. The one thing I don't like about it is that this starts with a negative sign. Well, we're so smart, we can fix that by multiplying through by a negative. So now if we distribute that negative 1, right, and again we distribute across addition and subtraction signs and across to the other side of the equation, we end up with negative times negative is the positive sine squared of theta, then minus the sine of theta minus 2 equals 0, right? Anything times 0 is 0. Now we have quadratic form, and we're going to solve this quadratic equation by factoring. So we're going to come in here and we are going to try to rewrite this as a product of 2 binomials. So we know that our first term needs to multiply to give us the sine of theta. So if we do sine of theta times sine of theta, that gives us sine squared of theta. We know that our last terms, right, what we're going to put here and here, should multiply to give us negative 2. So that means we'd have to have a 2 and a 1, with one of those negative, one of those positive. We know that we want our outers and inners together. Right? So I want my outer 2 multiplied and my inner 2 multiplied to add to give me this middle term. So if I make this 2 negative and this 1 positive, then my outers give me a positive sine of theta, my inners give me the negative 2 sine of theta, and those added together would give me my negative sine of theta, which is exactly what we want. So I'm going to come over here now, and I'm going to rewrite this, and I have my sine of theta minus 2 times my sine of theta plus 1 equals 0. Because this equals 0, which is so important, and I am multiplying two things to get 0, I know that if either one of them is 0, my sentence, my equation will be true. So this is going to be true if my sine of theta minus 2 equals 0, or if my sine of theta plus 1 equals 0. I'm trying to solve for theta. I want to get that by itself. Let's start by getting the sine by itself. So on this left equation, we're going to add our 2, and we get the sine of theta equals 2. On the right side, we solve for the sine of theta by subtracting 1, and we get the sine of theta equals negative 1. Well, let's think about this a minute. Can the sine of theta ever equal 2? No, the range of the sine is from negative 1 to 1. It's never bigger than 1, can't be true, so there is no solution, right? There is no solution to that equation. But can the sine of theta equal negative 1? Yeah, now you could solve that by taking the arc sine and then using your inverse sine, but isn't the sine negative 1 at, let's see, the sine comes from y, and the y is negative 1 at 270 degrees, or at 3 pi over 2. Because this is theta, we know that the sine of theta will equal negative 1 when theta is equal to 270 degrees. Now, my problem is that my domain was from negative 90 to 270, right? With a parentheses here, which means that I can't use 270, I can only come up to it. But, right, our trig functions repeat every 360 degrees. So my answer for theta is 270 plus 360 degrees n, where that n means I can add or subtract. If I take my 270 degrees and I subtract 360 degrees, I end up with negative 90 degrees. Negative 90 is in my domain, so that is my solution for theta. Okay? So just to recap what we did here, we started with the cosine and we replaced it with its Pythagorean identity so that we could get an equation with one type of trig function. We then took that equation as a quadratic and we factored it. We set each factor equal to 0, and then we solved each equation. And again, you can use your arc sine or inverse sine to do that. This was just one we could do by inspection. So that's one type of problem where we solve by factoring. Here's another situation, right? These are numerical solutions, right? If your equation can't be solved algebraically, which is true when your variable appears both algebraically within a function appears algebraically and within a function. So our variable is both inside of a function and outside of a function, right? Then we're going to have trouble solving that algebraically. When that occurs, we're going to solve it with our calculator from our graphing screen. So let me see if I can bring this down. All right, so here's our example. I have the equation positive 0.2x plus the sine of x equals 2. My x is being multiplied and added, That's algebraic, and my x is inside my sign. It's within a function. My goal in solving this would be to get the x all by itself, and I just don't have an algebraic way to do that. So we're going to solve this with graphing on our calculator. And the first thing we're going to do is we're going to go to our calculator and we're going to enter those functions. We're going to enter the left side as y1. So I have here that y1 is 0.2x plus the sine of x. And I'm going to enter the right side as y2. So I have y2 equals 2. And we want to graph those, and we want to look for where these two functions intersect. That's where our solutions will be. So I'm going to start with the zoom standard. So I'm going to come in here and go zoom 6. And there's that wave I expect from a function with a sign in it. And there's the graph of y equals 2. We can see on this screen that these two are intersecting at 2 points here and here. Right? And we could imagine that there would be more solutions if we went farther right in our window. It looks like our sinusoidal function, or a function that contains that sign, is kind of ramping upwards as we move to the right, where there are no solutions to the left, but there are at least 2 solutions to the right, maybe more. So I'm going to adjust that window so I can see farther to the right. I'm also noting that it looks like I don't need to see what's down here on the negative side of the axis, but I might need to see what's going on farther up. So I'm going to come in here to my window. Let me erase this so you can see what I'm doing. And I'm going to change my window so I've got x's from 0 to, let's try 15 and see what happens. And then I'm going to take my y's from just a little below 0, -1, to, I'm not going to go all the way to 10. Let's just go to 5. And let's graph again. So there we are with our inclining wave going up. We have our line y equals 2, and we can see now that we have 1, 2, 3 points of intersection. I wonder if we have more. All right, let's go back to our window, and let's go a little bigger. Let's make x 25, and let's graph again. Oh, with the way that graph is continually increasing, right, I run out of intersection points. I only have 3 intersection points. I only have 3 solutions. I find those by going to calculate, second trace. I want to find my intersection point. I'm going to move to one of those intersection points. I'll start with the one on the left. It really wouldn't matter as long as I find all of them. Right, I'm on my first curve, press enter. I'm on my second curve, right, where those two intersect, press enter. It offers me a guess, press enter, and I have a solution of 6.941. So my first solution here is that x is equal to 6.941. I would repeat this process to find the other 2. And if I did that, I'll just give you those answers. We would get 9.280 and 12.127, which are the location of all 3 of these intersection points. So again, just to recap here, we were trying to solve for x when set x was both inside of a function and connected algebraically through our normal algebraic operations. And just not being able to solve that algebraically, we solve it graphically with the aid of our calculator. We will do a couple of those tomorrow in class, and I know you're going to do a great job. Looking forward to seeing you tomorrow or over the weekend. After